I usually take some time, and I normally like to introduce a little bit of the theoretical background around these technologies. So I'm going to spend some time on that. Then I'll give you some just a few applications or devices and gadgets that we use in construction. But then I'll jump to more cutting edge or innovative applications that we are currently developing at our lab here. I believe I've shared a couple of papers for you to read prior to this presentation or in preparation to this presentation. And these are just a couple of examples of the projects that I'm going to be sharing today. Right. So like Dayana said, the presentation today is about virtual and augmented reality technologies in construction. So I'll be talking about principles, the applications and research. Just a little bit about myself. Like Dayana has already introduced me quite well. I'm actually an architect, but I did a master's in construction management, then a PhD in building construction, and currently, I'm a lecturer or assistant professor in digital built environment here in New Zealand. Not lecturer, sorry, senior lecturer. I've been promoted last year. And these are my my social media profiles, if you want to add me later. Just a quick summary of what or who Massey University is. We are located in the city of Auckland in New Zealand. It's a very nice, beautiful city, lots of sheep and boats and volcans and beautiful landscapes, and just a great country to live and to study. So please reach out if you are interested to learn more about study and research opportunities with us. All right, so also after this presentation, if you want to have a look, or if you want a good summary of mixed reality or VR, AR technologies in construction, just make sure to make sure to download this book and read chapter 7, which was written by myself and other authors in the Construction 4.0 book, that has been edited by my former PhD advisor, Javier Irizarry. All right, so let's start. I'm aware that you have been learning about multiple different technologies over this lecture series, right? Dayana told me that you'll be covering different technologies, like in this picture shows here. There's a prefabrication, autonomous construction with drones, etc., photogrammetry, IoT, the BIM, of course. So these are just a few examples, and today we'll be focusing on number 5, right? Right in the middle of the figure, augmented reality and visualization and virtual reality, of course. Okay, so if I'm going too fast, just please let me know. Okay, I'm just a little bit concerned about the time, so I'll try to. I'll need to go a little faster than usual. Right. So one aspect of the project delivery, right, is that we deal with very complex geometric information all the time, and that information is usually in the format of a BIM model, right, a 3D model. The thing is that 3D model carries critical geometric information, right? That information that needs to be reviewed and understood. So understanding that 3D model throughout the delivery process is a key for the successful completion of that project. And that's where advanced visualization technologies come into play. Advanced visualization technologies like VR and AR. Now, let's talk about the theory behind it, right? So extended reality, it's an umbrella term, right, that includes or encompasses advanced visualization and simulation technologies that are found anywhere between the boundaries of that continuum, that virtuality continuum, which goes from the completely real world, right, to the physical reality, this real world, right, to the completely virtual world, the virtual reality. The most popular examples of extended reality technologies include VR and AR. There are others, though. There are other technologies within that continuum, but we only use VR and AR. While AR, now the main difference is that while AR blends virtual and real objects, so it will mix or blend virtual and the real world. VR, on the other hand, is a completely computer-generated world, and there's nothing else other than the virtual elements in it. It's a completely virtual world. Now, those two techs, or actually all the XR, the extended reality technologies, they share three main components. The first one is the set of tools to develop and deliver the experience, right? So these this extended reality systems, they can have different configurations and levels of complexity. They can use different devices, different goggles, different headsets, depending on the application, depending on what you want to do with them. The second one is the information or the knowledge representation, right? Is the actual 3D model, let's say, the 3D model, the holograms, the scenarios that we are creating. And the third one, and perhaps the most important one, is the user, right? There's no VR or AR experience without the user. So when this representation, when the information, the content is processed by our brains, the result is the XR experience, right? That said, let's talk about each technology in more details now. AR first. Like I said, AR blends virtual and real objects by overlapping real-world images or spatial scans. We'll talk about that later, with virtual information. So we are overlapping real-world data with virtual data. Again, AR captures, collects, and overlays views of the real world, the real space, the real object, with digital content, therefore delivering an augmented experience of reality. We are augmenting the reality with an additional layer of information. Hence the technology's name. That's why it's called augmented reality, right? And how is this done? This is done using devices with cameras or sensors to capture real-world images or to capture real-world shape, right? In that case, we'll not use a conventional camera. We will use a special depth sensing camera or an infrared camera to scan the shape of the space, right? So what we need, in short, is a sensor to collect, to capture spatial data about the geometry of the surroundings. Once this data is captured, the software application will add virtual graphics on top of those images or on top of that spatial scan, right? As opposed to VR, AR allows for complete awareness of the real surroundings. So when you're using a tablet or a headset or an AR headset like that one in the figure, you know that you're still in the real world. You don't lose awareness. You're not immersed in a virtual world, right? There are different types of displays. We'll talk about that later. There are different types of AR as well, and different types of display. We'll talk about them now, actually. The display method, like I said, different types, and they vary between conventional touch screens or smartphones or tablets, right? Just your phone is an AR device, and see-through or transparent screens of these high-end smart glasses, right? Like, for example, the Microsoft HoloLens. These are called smart glasses that, instead of capturing real-time videos like the tablet or your phone do, they will scan the shape of the environment, and they will scan. So they have a tiny built-in laser scanner, which is actually an infrared camera, an infrared sensor. So they will scan the environment and place the digital content, the animations, in the correct scale, location, and orientation on top of the real world views, right? On top of what you've seen, or what you can see through the transparent screen, right? In either case, it's very important that these animations, the holograms, they align properly with the real world input. And how do we do that? So this is done by linking the virtual content, the animations, to certain points located in the real world. So we need anchor points. We need reference points for the software application to understand where it's going to place the animations, right? The digital content, the holograms. So the position, orientation, and scale of the animations are defined in relation to those points. To do that, those points in turn, they can be physical markers. So we need those anchor points, those markers. They can be physical, like QR codes, right? Like in the picture there, the top right picture, that's a QR code. In which case the technology assumes, or it has a different name, it's a different type. We call it marker-based AR. Now, there's another type if we are using GPS coordinates or spatial scans or spatial maps of the environment. That's called markless-based, markless AR, because it's markless, right? It has no marker, no physical marker. It's using an abstract marker, like coordinates or the spatial map, which is actually 3D mesh model, which is the result of the scanning, the 3D scanning, right? That the software application does. So in short, we need data from the real world, either QR codes, coordinates, or scans that can provide the anchor points, the base points onto which the augmentations, the animations will be placed, right? So this is just a very important technical aspect of AR that can be either a limitation, sometimes in construction, or a benefit. Okay, so depending on what you want to do in construction, you will need to choose between markerless or marker-based AR. To give you an example, let's see if this video will run. I'm gonna just turn off this. I'll show you an example of a markless AR that uses spatial mapping. I believe most of you have probably seen the Microsoft HoloLens, on the internet, or on YouTube, or maybe in real life. This is an AR headset or an AR smart glass that uses the spatial mapping technique that I mentioned before. Now, this is spatial mapping technique. It's actually called SLAM, that stands for simultaneous localization and mapping, which in turn is based on either photogrammetry, that you're probably going to talk about it later in this course, or structure from motion, or infrared scanning. So in short, just in summary, using this technique, the HoloLens will scan the environment to provide those anchor points for the alignment of augmentation. So you can see the lady there, she's looking around while, and while she's looking around, there's an infrared, HoloLens has an infrared camera right there on the forehead region between the eyes, that's going to scan the environment and create that 3D model of the environment, right? It's a preliminary 3D model. So again, it's a 3D, it's a spatial mapping or spatial scan. And that 3D model is used by the software application to understand the shape and understand where it's going to place the augmentations, the digital content, right? So that's spatial mapping. That's markerless AR. Just a fun exercise here. Actually, like I said, your phones, your cell phones are AR devices, right? If you go on Google and Google white shark, you can try that later. Google white shark or tiger or some popular animal, and then there will be an option there to see in natural scale, something like that. Google will show you see in natural scale, and you can click on that, and it will ask you to scan your environment. Like it will ask you to move your phone around, and it will be scanning the environment, the room where you are, and it will place the animal or a hologram of the animal in natural scale. It's quite cool. All right, so now let me show you another example. This is called Trimble XR10, which is basically, this is nothing very innovative or groundbreaking about it. It's basically a HoloLens attached to a hard hat, right? So if we put them both together, we can go to the construction site and we can project. Let me show you. And we can, no, let me skip to this part. We can project a construction manager, right? In that case, we'll project the 4D BIM model on top of the real world views of the construction site. So they can use this AR device at the job site to perform construction progress monitoring, right? Through visual inspections of the planned, the designed, against the actual completion of construction, right? You can project the 3D model, the BIM model, on top of the site and check whether the columns or the slabs or the walls have been built as per the design, according to the plan, or whether they have been built or if the progress is behind schedule. This is a very cool use of AR in construction. There's another one. This one here is more for facility management. In this case, AR can be very useful in facility management, like I said, providing maintenance personnel, the workers, the maintenance crew, with interactive visual overlays with instructions on how to perform certain tasks, right? For example, this could be visual diagrams and technical information overlaid on a real control panel, like you can see there, the arrows, the moving arrows, teaching them what to do, how to do the maintenance task, right? Which will allow them to repair much faster and much more efficiently, right? Yeah, so I think this headset, it's not available anymore, but it was my favorite actually. All right, another example of AR. This is also by Trimble. This is called Sight Vision. It also uses or projects a BIM model on top of real world views, but this one, it's video see-through, right? It's based on tablet. And it's basically a tablet with a huge GPS antenna. Let me show you the video here. There's a huge GPS antenna which gives the software information, well, the GPS coordinates, right? Information about well, the anchor points I was talking before. So it will give them, the software will feed the software with anchor points, and it will know where to place the BIM model very accurately, very precisely. And that's very useful on site before the construction works start. So they can understand, for example, the earthwork, the earthwork, right? Like how much earth or soil from you will need to move from point A to point B, and if there are any um, any conflicts or access to the job site, how to better plan for the construction works. Right. Okay, so another interesting benefit of AR is that it helps with the examples I just showed you. It helps to bridge the gap in computer human interoperability, right? When we talk about BIM, we talk a lot about interoperability, but that's computer, right? It's interoperability between systems, programs, software applications. Now I'm talking about computer human interoperability. That's the information sharing between computers and people, right? Think about this. Plans, sections, elevation, construction documents in general are traditionally extracted from BIM models, right? And those drawings are provided in hard copies at the job site to the construction manager or field engineer, right? This is how it works. That means that we are converting that very sophisticated three-dimensional and complex BIM model, three-dimensional information, into 2D drawings again. And in this process, there's a huge loss of information, right? So there's no interoperability between that three-dimensional information embedded in the 3D model and the person, the end user, right? Because we are fragmenting it into 2D drawings again. So I think this is one of the major gaps in the use of BIM in construction or 3D models in construction. BIM does help a lot in the design and planning stages and with all the other tasks and many other tasks, clash detection, automation of documentation process, and so on. But when it comes to construction or operation phases, we are back to last century. We are doing the same we did in last century or 4,000 years ago, actually. So the question is, how can we convey or bring this rich, complex information to the construction worker at the job site? And here's the link with augmented reality. Augmented reality, I just gave you the examples, provides a way for real-time interaction with the BIM model, right? 3D model, 3D information delivered at the job site in the real world. So that's very groundbreaking. I think that's an actual shift, an actual change and revolution to construction or in the construction sector. All right. So now virtual reality. Virtual reality, as some of you know, this is my main field of research. I'm very passionate about it, so I'll spend some time here. I've been studying it for 12, 13 years. So I'm very much interested in it, right? So, but before we move forward, I need to take a moment here just to delve a little bit further or deeper into the basic definition of VR, and the key concepts of presence and realism, right? Because there's a big confusion out there. If you Google virtual reality, there will be so many misconceptions and mistaken or incorrect definitions that I feel like being an academic scientist in this field, I feel the urge, the need to clarify that to you. So think about this. I hope you guys have watched this movie, that have seen this movie, this The Matrix. If not, just make sure to watch it, because this was one of my motivations to study virtual reality like 20 years ago. I've been always very passionate about this idea, which is the following. This idea that the world that we know is a mental representation, right? The world we know and we interact with is a mental representation that we create for ourselves using our senses, right? Vision, hearing, the all the 5 or 6 senses, right? And because these senses are limited, and by the way, the human senses, vision, for example, is very limited in comparison to other animals. Because they are limited, this world that we, may not be what we see, right? The world, the actual world may be something else, but because we can only see this certain spectrum or range of colors, so, things are this way because this is the way we can see. We're able to see. So this mental representation is not the absolute reality, is not the true, and will never be, because we're limited. So we live and learn from the interaction. We live, learn, we go to the moon, we go to Mars, we do everything we do. Uh, from the interaction, or based on their interaction with what we call reality, which in fact, again, is nothing but a mental representation, a mental model, right? So the Matrix, anyways, the Matrix movie is based on this tricky idea that our reality is also somehow, to some level, to some extent, virtual, right? We live in a virtual world, right? So this is the magic behind it. And anyways, enough of philosophy. In the technology field, in the technology domain, VR can be defined as the experience of presence in a virtual environment mediated by information technology. So I'm in turn, presence, just giving you more details. Presence is the feeling of being there, of being present in another environment, in a given environment, upon the perception of it. So presence is the result of perceptual cognitive processes, right? In short, VR is not the computer simulation. It's not a 3D model. Okay, it's not cool visual graphics, but a human experience of presence, immersion, involvement in the simulation, in the virtual world, which results again from the interaction among hardware, software, and our senses, our human senses. So, what makes a VR experience more realistic then? And based on that definition, it's probably the extent to which it can trigger my perceptions, it can trigger my behaviors, perceptions, and feelings that would be similar to the ones that I have in the real life, in the real world. So when I'm playing a video game, if I feel, if I perceive, and if I behave the same way or close to the way I behave in the real life, that means VR is realistic. And in order to achieve that, the virtual reality system, the simulation, may not need to be visually realistic. All right. So it's not about computer processing power. It's not about detailed 3D models or good looking renderings, right? Realism is a function of cognitive process. It happens within our brains. It's our brain that defines and gives the level of realism of virtual reality, right? There's a lot of research on that, some of which are my papers. So as opposed to AR, there's nothing else other than virtual elements. Like I said, it's completely computer generated. And that combination of devices, right, hardware and software, will provide us with that sense of immersion, the presence in a virtual world, through more intuitive and realistic ways of viewing and interacting with it. So to achieve that, we can use different configurations, different gadgets, different interface or interaction devices, right? And that results in a wide range of systems, of virtual reality systems, from non-immersive to fully immersive. The immersive ones, the fully immersive systems, they allow us to literally walk through the virtual space. We can literally walk, like physically. We can manipulate virtual objects using hand gestures and shift viewpoints with head movement. You look left and right, the virtual world will follow it, right? As if we were in the real world. And to enable high levels of interactivity, these systems will employ different combinations of interfaces or interaction devices that are able to engage different senses. They will also use stereoscopic head-mounted displays, body and head movement tracking sensors. Let me show you some examples here. This is the cave. The second one is also a cave. This one is just a multi-monitor semi or semi-immersive system. This is the headset that I just mentioned. This is the stereoscopic head-mounted display, and that's the most popular nowadays. And it comes with body and head movement tracking sensors, headphones for audio, data gloves or 3D controllers for object manipulation and navigation, and even treadmills like these ones. You can, like when I said you could literally walk through the virtual space, if we're using a treadmill like that one, you can walk around literally. So for each purpose or application construction, we'll need a different system. Now let's focus more on immersive head-mounted displays, because that's the most popular technology nowadays. And if you are planning on doing research or developing some VR application in construction, you're probably going to use some of these or of a similar setup, right? So these are just some examples of immersive VR HMDs or head-mounted displays. They come in different types, different sizes, different shapes, different colors. They're very affordable. Well, in comparison to caves, the caves used to cost back in the day over $1 million. This one is around $2 million, close to $2 million, right? Now, these headsets, they cost $300, $500. And also they require much less software and hardware handling, right? Most of them nowadays are wireless, and you don't really need to be a programmer or do some coding or anything too complex. You don't need to be a computer scientist, right? Yeah. So the setup and operation of immersive VR systems, like I said, nowadays is a lot easier. Unless you want to create very complex simulations in video games, and I'll talk about that later. That's one of my last slides. If you want to create something more complex, a simulation, of an accident, for example, of a disaster, a tsunami, of course, you'll need to use game engines. Well, I'll talk about that later. But if you want, for most applications in construction, for example, for design review, you only need to export the BIM model to the headset using a converter application, and Enscape, Qbity, or Iris VR. Those are just some examples of those converter applications. There are many other apps out there. Most of them will add a new tab, as you can see there, a new tab or button under the Adds In ribbon on Revit or ArchiCAD, whatever BIM software, authoring software you're using. So no need to use game engines, no need for rendering software or programming. So you can literally create your own immersive simulation in literally one click, right? You just click send or enable to send the BIM model to the headset, right? I'll show you a video here of Iris VR. This is a old video from Iris VR. This is a preliminary version. So basically, back in the day, it was a drag and drop app. You need to drag and drop the BIM model inside the interface, the software interface here, and this is the first view. You have like a bird view of a miniature of the project, and then you place your avatar there and you start your walkthrough. So you're immediately um, um, transported inside the building, and you can start your design review tasks, right? Once you are inside the virtual environment or that virtual building, it is possible not only to explore it, but also modify it. Some of the newer versions of these tools allow you to modify colors, textures, turn layers on and off, make annotations like that one, circles and little sketches, measure objects and extract dimensions and so on. And there's also an inspection tool to flag elements, or more recently, the multi-user feature. This is from, I think it's like 4 years ago. They added 3 years ago the feature, this multi-user option to enable multi-user or multiple users at the same time, inside at the same time, from different locations, right, inside the simulation. So you can have someone, you can be in Germany talking or exploring the building with someone from Japan, in Japan at the same time, right? So, and you can have hundreds of people at the same time as well. So that's pretty powerful. You can do your design coordination meetings remotely, literally, with your client, with the other stakeholders. And so a system like this has many applications, great potential. I would say most medium-sized to large-sized design office nowadays, they will have a immersive VR setup. They all have it. Everyone is using it. The medium and big offices, right? We can also use it at the job site, for example, to provide contractors and workers with a more accurate idea of the final geometry of the construction components, right? If they need to see how or what a staircase should look like when it's finished, they can check it out immersively, right? In an immersive environment. It could also be used to collect feedback from end users of a healthcare facility, for example, physicians and nurses. They can try out, right? They can have a try at the design, at the 3D with the 3D model, and check the dimensions. For example, especially for very complex designs like healthcare facilities, hospitals, it's very hard to determine the size of circulation areas, the size of surgery rooms, and we need feedback from physicians, from the doctors. So in general, VR can be very useful whenever you need to test or simulate something, right? Something that doesn't exist. For instance, design alternatives, like I just showed you, or how workers would behave in hazard situations or in a disaster evacuation scenario, right? It can also be used to create serious games. For that, right, in that case, we will need to create serious games, right, with which construction workers could, or could be construction workers, could be heavy equipment like crane operators. They can undergo hands-on training, right? We can use that system to assess how they would behave, or to teach them how to behave, right? To teach them what to do, or how to operate a crane, or what to do in a hazard situation. So they can undergo hands-on training in a virtual simulation, in a video game, let's say. We call it a serious game because the video game for a serious purpose, not for entertainment. So that virtual world, that virtual setting would mimic their experiences in a real construction site. So we can train them in hazard situations without exposing them to actual danger. That's a very powerful application in construction. There are lots of applications out there for construction safety training, fire safety training. We've been doing a lot of research on that. Disaster evacuation, yeah, and so on. I'm going to skip this slide. Recap. So just a quick recap, guys. I'll move to the research part now, but just a quick recap. So the blue one here is the virtual reality, right? So the virtual reality got the 3D model, we send it to the VR headset, and then there's the virtual experience, the resulting. In turn, for augmented reality, we have the 3D model, we blend it, we combine it with the real environment, and we put them both together, and that's sent to the AR headset. And that's the augmented reality experience where you have the 3D model, 3D animations on top of the real world or real world views. Oh, this is just a nice summary figure. You can find it in one of the book chapters we published about it. It's a nice figure to summarize everything. Basically, we have different, for the red one is augmented reality. We've got different types. As we discussed, markless and marker-based, different displays, the screens, also called video see-through, and the head-mounted types. These are optical see-through. We actually have some variations here, but this is just the general idea. For VR, we have different types from non-immersive to full immersive at different displays, like monitor, a projection-based, which are the caves that I showed you, the multi-monitor, like the crane simulator, or the head-mounted displays, right? All right, so I'll need like 15 minutes to go through. I've spent 50 already, so I'll just need 15 more minutes. 20 minutes maybe to finish the XR research part. Hope that's not too fast, guys, and too much information. I know, but this is recorded, so you can rewatch it later if needed. All right, so XR research. We've been talking about different VR, AR applications, systems, right? And XR solutions, right? They have been developed to enhance how workers perform in construction, in the built environment, in design, construction, or training. However, they often fail to consider how the end user perform cognitively when using such tools, right? We don't understand quite well what is happening in the brain. And we need to understand these cognitive processes because they are key to productivity and safety improvements. No productivity improvement will happen, no safety improvement will happen if people don't learn while playing or while undergoing a VR training, right? We need to understand how much they learn. We need to understand how better they understand the 3D model using a VR headset, for example. Otherwise, it makes no sense to have a headset. We need to measure that. Therefore, it's crucial to ensure that these tools can actually enhance our skills, enhance our cognitions, our cognitive process, our thinking. So that's what we do in human-computer interaction studies in XR, which are kind of a combination of basic and applied science, which also often involve challenging current assumptions regarding these technology solutions, and they will lay down the foundations of knowledge in this field. All right, so I'll start now with a few papers, a few examples of studies that we've been doing in this field. First one, we'll talk about some VR studies and then AR studies. The first one is this one where we wanted to understand how much, or the relationship between VR system and 3D spatial perception. So how much an immersive VR system would improve the understanding of the 3D model. Okay, so motivated by that question, we did, again, we wanted to know how effective the immersive system would be in communicating the geometry or helping people to understand the 3D model. So that was the main question, right? So we did an experiment. So we compared a non-immersive with an immersive system. We put people to walk through a 3D model in both systems, and we measured spatial perception, of a large sample of users. And we found that it provided an overall better spatial perception in comparison to no-immersive VR. So no-immersive VR is just a desktop system, right? It's just a conventional, traditional computer. And the immersive one is in that case, was actually a projection-based immersive system. It's like a low-cost cave, right? Back in the day, in 2014, there were no VR headsets. There were no VR headsets. The first one was released later that year. So we did with the projection based. So we found that provide a better spatial perception, therefore it can be considered the best representation technology, which in turn will facilitate collaboration and improve productivity and our buildings, our built environments. So see, we are addressing a very fundamental, a very basic question that if we improve this basic step, all the chain, it will repercute across all the chain. Will have effects through how the design or the delivery process, therefore, and at the end, will result in productivity gains. This is something important about the research. When we are comparing the spatial perception, we need to compare, we need to collect spatial perception of participants in the real world as well. But this is this is just a detail. Like I said, there were no headsets. So this is the operational framework or the a schematic visualization of the VR system we used. So here in the red frame here, we have the no immersive VR system, right? It's just a workstation, a desktop setup. And in blue, we have the immersive system. We send the oh my God, this is so old. We send the anaglyph, the 3D model, to 3 projectors, and these are projected. They will project the model on this panoramic screen, and then the user can navigate. It's quite old school. All right, so later on, a few years later, we did this study. We did this basically a very similar study. Actually, there were many issues with this first one. So we did a second one. We kind of revised the first one. And here we used a headset, right? Because headsets were very popular and caves were outdated, and we did with a headset. We did the same, the same question. We wanted to investigate the effectiveness of a fully immersive VR system with a headset in helping people to understand the 3D configuration, the 3D geometry of a BIM model. And we found that it also offered a superior 3D perception, 3D understanding compared to the non-immersive system. We call it three-dimensional perception. That's the technical term. And we also needed to. This is just the research design framework figure. We also needed to collect people's perception in the real world as well. This is just a very important detail. Whenever I'm talking about in more details about these studies, I normally spend some time explaining the experimental design, but not the case today. The next research, this is about, this is an ongoing project. Right, so we're still working on that. Fire safety, right? Fire safety training is essential in different contexts, right? Especially and including in the built environment, right? We need to train people how to operate a fire extinguisher, to put out a fire. We need to teach people how to exit, how to evacuate a building in case of a fire, right? So this is fire safety training, right? And there are several methods or tools to train people on safety. And these include virtual reality, right? We can also train them with lectures, right? With presentations. But virtual reality can be used for effective training. That's one thing. This training, in addition, this training needs to be periodically refreshed because we forget, right? So we need to train over and over and over so we retain the information. But the ideal intervals for retaining are unclear. So each country will have their own policy of, refreshment training. For example, for site workers here in New Zealand, I don't know the interval, but I think it's once every year. But those intervals are very random. Nobody knows. Nobody knows how much or how often we need to train people so they can, not forget. And so to address this gap, this is the first study ever done in the world. We have started this project which is funded by the Royal Society to look into how well people retain information from different training methods, including video-based or just watching a YouTube video, VR-based, and real-world training, training in the real world. So we are comparing these three types of training over time. So it's a longitudinal study. We'll assess, we'll evaluate the participants' knowledge along with, and there are other variables as well, learning performance related variables. After training, then after 3 months, then after 6 months, then after a year, and at the end, we'll have this forgetting curve. For each training method, we'll be able to draw this model, this forgetting model, right? That will help us to identify which one results in better knowledge retention, which type of training results with better knowledge, in better knowledge retention, and understand or determine the optimal frequency of the refresher training. So if you are training with virtual reality, you need to train every 3 months, for example, or every 1 year. Or if you're training with a YouTube video, you need to train every week because you forget fast. You see, that's the point. So let me show you the simulation we designed. This is actually a simulation. Well, the training for this project is how to operate a fire extinguisher to put out a fire. So there's a set of steps. I'm just gonna mute here. set of steps. So this is the view you have inside the VR headset, right? This is the serious game. This is the VR training. Oh yeah. So to design that, to develop that, we actually need game engines like Unreal or Unity. Those are special software applications that are used to develop video games, right? This is much more complex than the converter application for design review. Okay, so the next project, I'm almost done, guys, just 4 more slides, is this a very cool project we just finished last year, in which we basically created, let me explain it first. We basically created this AR, now it's AR, augmented reality, fire safety training system to help people handle fire emergencies. So help people evacuate, or to train them on what to do in case of a fire, how to evacuate or exit a building on fire, right? So, or a room on fire. So we developed that system and we compare it to conventional video training, like YouTube videos, to see which one is better, right? So again, AR training was way better in terms of motivation and self-efficacy, which are learning performance metrics. So this research shows, how this new tech can totally change the game and safety training, not only AR, but VR, not only VR, but AR as well. So let me show you the system here. Oops, it's too loud. So this is the view the user has inside the Microsoft HoloLens, which is that AR headset, optical see-through headset, right? Optical see-through AR, sorry. So that firefighter, that floating firefighter, will give the instructions to the user on what to do in case of a fire. So first steps to find the fire, to identify the fire. That's it. So basically a few steps there showing what to do in case of a fire. In this case, this is a fire safety training tool, but could also be, once we know what these technologies do after this class, now that we know, this system could also be used for during the fire. Imagine if you have, instead of a safety vest, if your building is on fire, you put on your Microsoft HoloLens, and we will guide you on what to do. Right? It will guide you through the best route, the best path to exit the building, or in what to do. Right? This can be also a tool during the fire. This is the experimental design. We have 2 experimental conditions: AR training, video training. This is more HCI stuff. We have a pre-training questionnaire, then the training session, then the post-training questionnaire, and then 4 weeks later. This is now the AR system framework. This is how, if you are more interested in the technical details, right? There's a calibration stage, there's a marker detection stage, which are detected by the HoloLens, and which in turn will deliver the augmentations in the real world or on top of real world views. Now, this is another project we are working on. This is the last one, I think. Yeah. Yeah, last one. This is about, it's very similar to the VR projects. So it originates from the same idea, the same reasoning as that. So it's also important. Let's put it this way. It happens that a fundamental assumption of AR applications, like the ones I just showed you, is that the presentation of the virtual elements, the virtual objects, the animations, is sufficiently realistic, right? In order for those applications to be efficient, in other words, let me rephrase that. In order for AR simulations, applications to be efficient, the objects we are seeing, we're looking at, they need to look realistic. Obvious, isn't it? It's obvious, but nobody has ever checked that, right? It is an assumption. It remains an assumption, remains untested. So we do not know how, we don't know whether AR can accurately convey geometric and spatial information. We know that about VR, right, with the studies I shared before, but we don't know that about AR when it comes to AR. So in this study, we'll compare different types of AR tablet, AR head-mounted display, and different types of display. One tablet and two different displays. So let me show you. This is a visualization of construction objects, right? A safety cone, a metallic beam, a concrete block, through Microsoft HoloLens. So we scanned those objects, we created 3D models of it, and we are projecting on top of real world views. And now with that set up, we are measuring three-dimensional perception to see which device, which type of AR delivers better or more accurate three-dimensional geometry. And this is just the experimental framework. We'll compare with real world perception. Very, very, very important. Yeah. And that's basically it. It's 1 hour and 10 minutes, not too bad. This is our website. Okay, if you want to learn more about our projects, there are very few projects. I need to update the website, but there are like 5 or 6 projects, but the major ones are there. There's a list of people that work in our lab, the Digital Built Environment Lab, which is one of the labs of the School of Built Environment of Massey University, where we work. We are a group of around, I would say, 12 faculty members and maybe close to 20 PhD students. That's a big group. We are all doing something related to digital technology, drones, reality capture, laser scanning, virtual reality, augmented reality, building information modeling, BIM. There are other, some students are working on artificial intelligence, with artificial intelligence applications. Yeah, so please reach out, make sure to visit our website later. And that's all for today, I think.